As I said, yes, so in this session, I want to discuss the situation with the diffusion, with the added noise. So I remind you, okay, so now the case with added diffusion. So I'm going to still focus mostly on first order systems. And I remind you that in this case, we think of things in terms of the density, the probability law on configuration space, Fn of x1, xn, which solves the Liouville equation dt_Fn plus the sum over I of divergence with respect to variable xi. And here you have the interaction. Fn, okay, equals one over beta. So I normalized things that if last time at first lecture I got a 1/2 beta. So let me just change 2 beta into beta. So we don't have a 2 that's floating. And here we have a sum of Laplacians of Fn. And we have convergence, expected convergence to mean field equations, which is sometimes called Fokker-Planck or McKean-Fokker-Planck in this context. T rho plus divergence k convolved with rho times rho equals 1/beta Laplacian of rho. So we have the extra diffusion term here, Laplacian of rho. Okay, so I want to discuss the relative entropy method, which is much older than this modulated energy method that I discussed, but in a way it's of similar spirit because as we said, it's again a way of finding a sort of good distance between the discrete solution and the limiting continuous solution, so relative entropy method. And I'm going to discuss to make the computation and also discuss the recent work of Jabin and Wang, how they are able to treat certain singular kernels, right? So the question here is again, when k is not regular, what can you do? And we've been focusing so far on the case where k is related to the gradient of inverse power, for instance, but it doesn't have to be. So just do that. So let me remind you what the relative entropy is. So in this context, what we're going to compute is the relative entropy of Fn with respect or relative to rho tensor n times, and normalized in this way with the 1/n in front, integral of Fn log of Fn divided by rho tensor n times and integrated. Okay, so the method is the same idea. You have to differentiate in time and hope that you can close a Brandval relation. So let us do the computation just so you see what it looks like. Okay, so first you have to differentiate in time Fn, multiplied by this. So I dropped the xn here, but and second, you have to differentiate log fn. So you're going to have 1 over n equal of fn dt fn divided by fn. So that's when I differentiate the log. And then when I differentiate the log rho tensor n, I get fn dt rho tensor n times divided by rho tensor n times. Okay, so here you see immediately there is a simplification between fn over fn. And because fn is a probability density when you integrate dt fn here, it's dt of integral of fn, that's 0. Okay. So this is 0, 0 because dt of integral of fn is 1. So this is 0. So I just have 2 terms to compute. Okay, so there's going to be this thing going to be called 1. And this thing is going to be called 2. Okay, so what is 1? Well, for 1, we're going to just input the Liouville equation. You see, we have an exact formula for dtfn. So we're going to input the equation. So we have the integral of log, let's say log fn divide, sorry, log fn divide by rho tensor n times. And here we put the equation. So 1 over beta Laplacian xi sum of k fn. And of course, this is sort of calling for integrating by parts, applying Green's formula. So we do that, and when we have the Laplacian, we hit this log with a gradient. So there's going to be 2 pieces when you differentiate log fn. So it's going to be gradient. So sum over I is going to be a gradient of log fn. So that's a gradient of fn. But here there's going to be another gradient of fn. So it comes with the square divided by fn. And then the other one is going to give you, let's say, the divergence. So sorry, the gradient is when it hits the log of rho tensor n times. You can do a little computation. So maybe I will do that first. Computation. Like a remark, which is that when you compute the gradient with respect to variable I of log of rho tensor n times, well, you're computing the gradient of rho tensor n times divided by rho tensor n times. Let's not worry about possible vanishing. So here you have a product, rho of x1, rho of x2, rho of x3, and when you compute the gradient, it's just going to differentiate. So you're going to have rho of x1, and suddenly you have grad rho of xi, and then you have rho again, and you divide by rho. Okay, so when you do this thing, it simplifies, and you get just actually you just get grad rho over rho of xi, which is the same also as grad log rho of xi, right? So this is the difference. Is just that this is the gradient of a function that lives on Rd to the n, whereas this is a gradient in Rd, right? So this is gradient in Rdn. This is gradient with respect to just one variable in Rd. And in the same way, if you have a dt log rho tensor n times, you will find just dt log rho of xi. Okay, so now when I have this divergence, I hit the log rho tensor at time with the gradient, I just get gradient log. So I would get just integral of gradient log rho of xi. And there's going to be a sum over I. And this comes with a minus. So let's see. So this is plus, so there should be a minus. I'm not wrong. And then what do? I have sorry, it's a plus. Gradient xi fn. So this is for this term with the derivative hitting this log of rho tensor n times. And then I have this term and I put the divergence on the log again. So I'm going to have two more terms. So I'm going to get a term like 1 over n integral of sum over I grad I fn divided by fn dotted 1 over n sum over j different from I k xi minus xj fn. And I have the last term where this hits the log rho tensor n times. So as we've seen, this is just log rho xi dotted 1 over n fn. Okay, so we have 4 terms. And we have a little simplification again here. We can simplify those two things, just formally. And we'll leave it at this for now. And we're going to compute the second term. So you see the second term that was here. So for the second term, we use the dt rho tensor n times divided by rho tensor I times. That's dt log rho tensor I times. So I just have to compute dt log rho. And for that, I have the equation on rho. Okay, so number two equals minus 1 over n integral of fn sum over I of dt log rho. So that's the same as dt rho of xi divided by rho of xi. And I use the equation. So minus 1 over n fn. And here we have a sum over I 1 over beta Laplacian rho of xi minus divergence k convoluted rho times rho, all of this of xi, and we need to divide by rho of xi. Okay. So again, some integration by parts. There's going to be a term like this, where now we have gradient fn. So I take the Laplacian and I hit fn with the gradient, right? So I get gradient rho divided by rho. And then I have the Laplacian, I can hit the 1 over rho. So for that, I get fn sum. So gradient rho, gradient 1 over rho, it's going to give me another gradient rho divided by rho squared. I'm going to get a gradient rho squared divided by rho squared. And because I have a minus here, I'm going to have a plus. So this is another integral. Okay. And then I have the last term. So for the last term, integrate by parts again. So let's just leave it like this. So what I'm going to say is that this is minus 1 over n, sum of Fn, sum. So I can expand this divergence of this product as the divergence of k convolved with rho coming outside, and then it simplifies. Right? So it's going to be divergence k convolved with rho at xi. And I simplify the rows, but then I have to have another term, which is minus gradient of rho dot k convolved with rho. And that gets divided by rho. So here there is a plus. Oh, it's clear. All right, so now we're ready to add 1 plus 2 dt of the relative entropy. So it was 1 plus 2. Guess I'm going to copy all the terms after the simplifications. And we're going to group together the terms. So you see these terms like that. We're going to try to group them with terms like this. For example, all the terms that involve the gradient of Fn are going to be grouped together. So I copy here. So the terms involving gradient of Fn. And there is one like this, one like that, minus the sum gradient Fn, gradient log rho again. So in fact, I have 2 of this. Let me put them right away. And here you see I recognize gradient log rho squared from here. You see here there's gradient log rho squared. So I can put it in this form. Okay, so this is one piece. And then for the second piece, I have an integral sum of gradient I Fn dot 1 over L sum of k xi minus xj. Then I had a 1 over n integral of sum. So here you recognize gradient log rho. And write it like that. This is a cross term, and then the final term is the last two here. Minus 1 over n equal Fn sum of div k convolved with rho of xi minus gradient log rho of xi dot k convolved with rho of xi. So I have a sum of terms here. And the idea is first to recognize here a perfect square. If you look at this thing, if I'm not mistaken, I'm going to be able to rewrite this first sum of 2 terms. as integral of fn sum over I, and here I have gradient log fn minus gradient log rho of xi squared. So look at this. When you have gradient log and you take the squared, you will have grad fn squared divided by fn squared. And if you remultiply by fn, this is exactly this term. It looks like a Fisher information, in fact. And then you have the cross term, grad fn dot grad log rho divided by fn. That's exactly these terms. And then the third term is exactly this term. So you sort of recompose here sort of relative Fisher information. When you differentiate an entropy, typically you get these Fisher information terms. And here it's relative because it's really, it's the gradient of log of fn divided by rho tensor n times. That's happening here. Okay, and then the second term. So let me see if there is any little simplification, but not much. So we're gonna group things like this, integral of fn, sum of divergence. So here you have a bit of a choice, and I'm going to try to discuss that. We have terms like this. Dotted with the same difference. Okay, so this is the end of the calculation. So you see what I've done here is I've taken this piece and actually, this piece and actually integrated by parts again. So put everything in factor of fn and put the divergence onto the right-hand side. And there is another term like that. They convert with rho. That you can group with it. So you see you have fn with some divergences here and here. And then you have the other term, one is coming from here and one is coming from here. You can group them together. So this divergence, you can also basically put it back on fn and have a gradient. Yeah.
But you probably put one more divergence in this row.
Yeah, sorry. So okay, I took two divergences. I should do, if I want to be correct, I should remove this parenthesis. Okay.
Yeah.
Is it good like that? Thank you.
And I think there's no one more divergence, right? Divergence K convolve. That's fine. Oh, now that's fine.
I think now it's fine, right? Because this divergence here is only hitting this guy, and this divergence here is hitting that guy. So you see the parallel, right? This is a sort of discrete version, and this is a sort of continuum version, because if you believe that the empirical measure is very close to rho, this term is well approximated by this term. So you get this discrete version, continuum version, etc. Okay, so very good. So now, can we control this? The question is, can we control this by the relative entropy itself? It's not looking so obvious, no? So, well, definitely you have this negative term, which is good. You could drop it, but it's not very smart to drop it. You should actually save it because it's going to be useful to absorb other terms in it. And then you have these terms in the form of fn times time things that are not not necessarily super nice. So if K was very smooth, it would be okay, but what are you going to be able to do? So the main tool is convexity inequality. So the way to do it, there's not many tools at your disposal, is to use a convexity inequality, which is a formula a bit like a convex duality formula that allows you to basically make a change of measure. So I write it in the way it's written in the paper by Jabin and Wang. If you have any function phi of big xn, dfxn, and if you want to compare the expectation of phi under the law Fn, this is right, this is like expectation. This is expectation of phi under Fn, if you want. You want to compare that to the expectation of phi under rho tensor n times, under the other law. Right, so let's, so the inequality that you have is that you can control this by Hn Fn relative to rho tensor n times plus, okay, so you would hope that you control in terms of the expectation of phi with respect to rho tensor n times, but that would be too much to ask. But you control by something which are the exponential moments of that. So you're going to put a 1 over n log integral of rho tensor n times e to the n phi. And because you could sort of stick in 1 over eta and an eta in a convexity inequality, you have a little parameter that you can add if you want. So we're going to put 1 over eta times this, and here there is an n eta. Okay, so for every eta parameter. So you can check that the scaling allows you to put these n etas if you want, here and there. Of course, you could decide to just take eta equals 1, for instance. So this is a fairly standard convexity inequality. It just is based on the convexity of entropy, and you can find it in probability textbooks, but you can also read it in the paper. So in Jabin Wang, they have a proof of it. It's only a few lines. But so what I want to emphasize is it's really a general fact, and it's really a question about comparing expectations with respect to two different laws, right? So if I have two different laws, Fn and Fn prime, and I know the relative entropy of Fn with respect to Fn prime, so it's a sort of distance, then I can control in terms of the log of the exponential moments, if you want. So that's my second law. Right, so this is a much stronger version of the expectation of phi under Fn prime. This, you don't control just the expectation, you control all the exponential moments. So basically the price to pay for going from the law Fn to the law Fn prime is that instead of controlling the mean, you have to control all these exponential moments. But maybe you're willing to pay that price because now you can control in terms of the relative entropy. So it's this for arbitrary Fn prime. So here Fn prime is rho tensor n times, but it's not important. Okay. So now if we try to apply this trick, we see that we're computing the expectation with respect to Fn of these complicated expressions. We are, of course, going to assume that rho is nice, right? Just like in the modulated energy method, we can assume, and it's actually the case because we have a Laplacian now in this equation, that rho is nice. So anytime I see grad log rho, I'm not worried. This is a nice smooth thing. Even my k controlled with rho, this is nice. Those things are more worrisome. Right? So let's see what this does. So what Jabin Wang do is assume that diff k is also nice. So they assume diff k is bounded and k is divergence of v with v bounded. Okay, so if diff k is bounded, then that's actually good for this term. Now you start to get something. Okay, so we have to control these two terms. Let's try to copy them. So you see, with this point of view, it's not a good idea to do this integration by parts. You should you exploit the fact that diff k is nice, so you leave it like that, and then you just have terms in Fn. So we're going to be able to bound by the convexity inequality. We're going to bound this by, of course, the relative entropy. And then these exponential moment things. So, right, so we're going to have the log of the expectation. So it's going to be these integral with respect to rho tensor n times of these quantities. So how do I want to write them? Exponential. Yes. So there's going to be a term. So if I'm not mistaken, and I have the expert in but so for the terms that are in diff k bounded, you have these things that involve diff k, right? And for the term that's below, you're going to use the fact that k is diff v. So with this diff v, you can do some integration by parts and take this divergence to Fn. So I should have done this before. So there's some terms like that. There's some terms here that are going to be bounded in terms of derivative of Fn times v, because you integrate by parts. And now we have to remember that we control this thing. We control this relative Fisher information, and that controls for us gradient Fn squared somehow, right? Because if I write grad log Fn as grad Fn squared divided by Fn squared, I have some control of grad Fn squared. So this part eventually gets absorbed into the entropy dissipation. So I remember you keep these negative terms, you don't throw them out. Or if you want relative Fisher information. And the other part, you get yourself with additive terms. So, you get absorbed, except that there is an error, an additive error term, which I'm going to write below, which is again obtained by this type of convexity inequality. So another exponential moment of something that looks like this. Okay, so what they do in this way is they reduce the question to controlling these exponential moments or these partition functions. Control these, basically you can call it log of partition functions. So these are like basically, these look like, I should have an exponential, I forgot my exponential now. If you know a little bit of statistical mechanics, these look like partition functions associated to Gibbs measures for interactions of the form of the kernel V. So you see you have exponential of the interaction, and then you integrate this with respect to the reference measure rho, but rho is regular, so it's as if you were just sampling your points in like a Poisson way. And so you need to control this in terms of n. See how fast does it grow in terms of n? And this is a standard type of question in statistical mechanics. So they call this large deviation estimates. And this is a big part of their paper, is to control this the growth of these quantities in n. Okay, so maybe I have some 1 over n that's floating. Yes, you see I have this 1 over n, so I should definitely keep these 1 over n's here. Otherwise it will be too big. Okay, so one part of the problem, whenever you need to use gradients of Fn, you absorb by the entropy dissipation. And the other part, you use this convexity inequality to control by, again, the relative entropy plus some free energy or log of partition functions that you control separately. So this is a separate work that is quite delicate. Okay, so in the end, you can show like this what you wanted, which is that Tt of the relative entropy can be absorbed by the relative entropy itself, plus something which is well controlled, plus, I think it's O of 1. Okay, and with Grandval, we finish. And I remind you that once you control this big relative entropy, you control the relative entropy of or the K-point marginals, thanks to the subadditivity relation. So if you control this one is bounded, then you're going to get, for fixed scale, you're going to get good convergence of the K-point marginals. Okay, so important remark, in case you haven't noticed, important in all this, we really need beta to be finite and not infinite. Because we absorb a piece of the derivative into this Fisher information. And the Fisher information has a -1/β in front. So if you go back somewhere, yes, you see here, there's a 1/β. So if beta is infinite, we won't have this term, we won't be able to absorb. So the relative entropy method is really a method that relies on the noise. So we need noise. And it's because if you had just pure noise, if your evolution was just the Brownian motions, then the relative entropy is the perfect quantity. It's exactly what you need. And when you add the interactions, well, it's sort of a perturbation of that, and you can finally absorb this as errors if you want, but it's based on what's happening for the pure diffusions. Okay, so we need beta finite. The other comment is that with this, so they had these conditions. You may wonder, okay, which kernels satisfy these conditions? So certainly this can accept a little bit of irregular things, because you see, K is the divergence of something bounded. So K could be quite irregular. So this leads you to something like W -1 infinity as a condition. But you have this extra condition. So it's a trade-off. But what's striking is that with that, you can treat the Biot-Savart kernel. Okay, so this Biot-Savart kernel, which is the grad perp of log of x, arises in the Navier-Stokes equation for points from the point vortex system. So it's point vortices in 2D. Yeah? So with the added diffusion, it converges to Navier-Stokes. Convergence to Navier-Stokes. So why is it that they can do it? Because it happens that even though it's not very obvious, but in a vector manner, they can write this as a divergence. So as a divergence of something bounded. So this can be put divergence V with V bounded. So it's a strange formula which involves some trigonometric functions which I forgot, but you can look at the formula and see that by computations, it is true that it can be put in this form. Okay. So it still does not handle Coulomb in higher dimension. So it's a very particular case of sort of Coulomb in 2D, but only in the conservative setting where you do the grad perp and not the gradient. But not, not K equals grad G, G Coulomb, or grad perp G, G Coulomb, D bigger than 3. The singularities are too strong for that. Okay, so this is this is sort of the limit of what you can do with just the relative entropy, but I want to emphasize that it really involves the temperature. Okay, so now I want to make a little comment, since I have something like 10 minutes left, on also another quite interesting recent work by Daniel Lacker that sort of improves on this relative entropy point of view. So not for the singular case, so he's not particularly focused on K singular, but on the regular case. So this is on the more classical regular case. Okay. Okay, so in this in the more classical regular case, what people do is they don't try to put the divergence on K, you know, to exploit the fact that here the problem is that K is singular, but divergence of K is better than K somehow, right? So you see here, divergence of K is better than K. So that's why you keep the divergence here. But if you don't have this issue of K being singular, then you prefer to actually integrate by parts and put the derivative onto F and then absorb part into the entropy dissipation. So this is what we come back to. So this time, not put divergence onto K, but keep terms of the form grad F times K. And then you do this absorption into entropy dissipation. Plus this convexity inequality. And you're able to obtain things like this with the additive error terms, which this time are of this term, of these forms. Exponential. Okay. So what Dan Lacker was interested in doing is improving the convergence of the K-point marginal. So Lacker improved the convergence of K-point marginals. So I told you by additivity, we could get that H, F, and K relative to rho K was less than K over N. So C K over N, let's say. And what he shows is that this can be improved to C K over N squared. So that's a little bit surprising somehow, because you would think that when you do this this inequality here, you haven't lost very much, but in fact somehow you have, and you're able to show, or he's able to show, that the rate of convergence, if K is big K is nice enough, is actually K over N squared, much better than 1 over N. So he calls this local propagation of chaos as opposed to global. Local propagation of chaos. So local in the sense that it depends. It's the estimate you get when you only look at a few particles at a time, right? You want to look at K particles, so 1, 2, 3, 3 particles, and you don't try to understand what's happening with all the particles at the same time. So it's local in terms of these few particles that are the center of the attention, I think. So what he observes to prove this, that if you let hk, h superscript k, denote for shortcut this relative entropy of the k-point marginals. If you differentiate in time hk, you compute, well, there's a certain number of computations, maybe I won't give them to you, but in the end, you get something that scales like k over n squared plus ck hk plus 1 minus hk. So this is the important inequality. Okay, so at first it doesn't look very good because you're like, okay, in order to understand the derivative in time of hk, I have to look at hk plus 1. That's the hierarchy aspect, right? We encountered this before. If you want to understand the k-point marginal and the evolution of the k-point marginal, you're going to have to look at the k plus 1 point marginal. And how do you get anywhere with that? And so here you refine this fact that you need to understand the k plus 1 relative entropy. But the point here is that you also have a minus hk here. So when you have a ground val inequality, right? If you look at ddt of hk less than minus hk, this is actually very good. This is exponential decay, right? If you just had this thing and this thing, you would have an exponential decay built in it. And so what he's able to do is to say, okay, I have the exponential decay plus maybe this growth due to the hierarchy. And he's able to basically control this term by going to the last term in the hierarchy, which is hn, which you can control, which we know can be controlled in a very rough way by O of 1. Okay, so this is the idea, right? So when using ground val, so when looking at this sort of ODE, the very important part is this minus hk here. So the minus ck hk term brings exponential decay, while the hk plus 1 term can be controlled iteratively. In terms of the last guy in the hierarchy, hn, for which we have these bounds that we've seen already. So I think the bound by O of 1 suffices. And so when you put that together, there's a sort of a bit complicated ODE argument. So that you can consider a crude estimate. And there's a complicated little ODE computation, which eventually can be concluded into this k over n squared, right? So eventually get hk to be less than k over n squared, which is better than k over n, and which is sharp, as he shows. It's actually sharp. You can check in some Gaussian cases, you get exactly equality. So you cannot do better than this. And so it's a nice, very nice thing. And the computations that lead to this are of similar nature. You have to compute the derivatives of this, but you have to regroup terms in a smart way in order to see this difference. that appears. And so I can make one more comment before finishing for today, which is what are his assumptions on K? Well, if you look at his assumptions, you'll recognize very similar things to what we've discussed before. So he assumes, he asks for K. Something like this, the soup with a T of integral of exponential C K minus K equals rho T. Square of T rho T is finite, or he asks for this and he says that this one implies this one. So this one is weaker. So for every probability nu, you want the difference between nu K and rho Tk to be controlled in terms of the relative entropy. So if you want to control a difference like this, you can try to apply a convexity inequality, like I showed you. So right, this is the law with respect to nu or versus the law with respect to rho. You bound by the relative entropy, and you get some exponential term. And so he shows that if you control the exponential terms, it's enough to control this. And so this is certainly satisfied when K is bounded, if I remember correctly. And it's, if you go back to the proof that I've discussed before, right? So it's what you need if you want to treat these terms without putting the divergence on the K. So without assuming that this K is good, if you keep the divergence on the Fn, you still need to assume something on K. So typically K bounded would suffice. So, you know, it's not as singular as what's treated in Jabin, but it's definitely less stringent conditions than what's in the classical literature, you know, Smitman, etc., where it always you assume that K was Lipschitz. So this is starting to relax also things on that end. Okay, so next lecture on Monday, I think. I will finish with this by showing you how you can combine the modulated energy method and the relative entropy method to treat both the singularity like Coulomb and the noise. So this is based on work of Bresch, Jabin, Wang, but now we have all the ingredients. I can explain that to you relatively quickly. And then I think there might be some time left. So I could either stop there, or I was thinking of maybe giving you a little bit of a flavor of how the tools that I've described so far can also be used in the context of statistical mechanics to understand the Gibbs measure associated to these Coulomb gases or these gases. So the sort of statics, if you want, of these or invariant measures associated to these systems. That's good with you.